Welcome back to another episode of Adventures in Machine Learning. I'm one of your hosts, Michael Burke, and I do data engineering and machine learning at Databricks. And I'm joined by my co-host,
Ben Wilson. I write release notes at Databricks.
Today we are joined by a guest named Lukas Geiger. He studied astrophysics in university and then entered the workforce at Mozilla and now at Plumer AI, which is spelled Plumerai. And he also has a really impressive suite of open source contributions. For instance, Lark, which is a quantization focused neural network training library, and then also the underlying compute engine for Lark, and then some other contributions like TensorFlow. It's the small repo that I think I've heard of. So, Lukas, can you explain what surface detector traces are and why you'd use adversarial networks to refine them?
Yes, it's been some time. Hi. In my master's, I worked, in my master's thesis, I worked on an experiment called Piaget Observatory, and it's basically an array of like huge water tanks somewhere in Argentina, and the idea is to basically study what kind of cosmic ray particles sort of come into our onto Earth. So we have like galaxies and stuff that accelerates particles, and any moment in time we get like mostly protons that come into our atmosphere. They interact with the particles there. And a thing called like an air shower emerges. You basically get like a cascade. And on Earth, we can sort of detect these secondary particles. It's done like with these giant water tanks. So these particles do something called like torrential radiation, which you then can detect there. And we used machine learning to study the underlying particle that induced this basically air shower. And so you can measure a couple of different things there. It's like just the arrival direction, which basically you can get from the time information of like a shower front arriving at the Earth's surface. The total energy, which more or less is the amount of signal that you get there. And one thing that's sort of new is you want to try to know the mass of the particle, like whether this is, I don't know, carbon, or whether this is just hydrogen, or like the core of hydrogen atom. And simulating this is all very, very hard and very difficult. And there basically I tried to use generative adversarial networks to adapt the simulated data to more accurately reflect the real world sort of measured data, train supervised models on top of that, and try to predict a value called X max. It's basically the maximum of the air shower. Sorry if I've been a bit confusing. It's been some time since I worked there, but that experiment had direct measurements for like a small subset of events, which meant we could do like lots of this machine learning craziness, and then in the end have like a really independent measurement, which would allow us to evaluate and sort of properly test that to also check like what sort of the error is. I only worked there for like a year, but that was very exciting.
Cool. So let me see if I understand. I'm picturing Earth, it's like a blue ball, and we have an atmosphere, and there's sunlight coming in. Those are particles, and we have carbon, whatever, hydrogen. They're interacting with each other, and when they hit the Earth's surface, we create a little swimming pool, and that swimming pool will then measure how they interacted. Is that about right?
So basically what arrives here at Earth is mostly then sort of the the end product of the particle
the
physics
collisions.
of all the particle physics interactions, and that is mainly muons and electrons. And if you have like a large body of water, that's what these Cherenkov detectors are. These particles have a velocity inside this medium water that is higher than sort of the
speed of light.
Exactly. That's what
Yeah,
I was looking for, and that's basically what gives you like this little blue glow. If you ever seen like video of like nuclear reactors, that sort of Cherenkov radiation. So you basically get like photons that you can measure with like PMT tubes. So basically, just get a signal and see. So this is like an event. But it's very hard to distinguish between muons and electrons, and that's why I try to use deep learning, because otherwise you need other detectors, which I think they've upgraded now as well.
So that's almost similar to the detection protocol that they use for neutrino detection underground, right?
Yes, it's pretty similar.
Where you're basically trying to measure particles traveling through interstellar space at near relativistic speeds. What does it happen? Like, what happens when it encounters matter? That's fascinating, man. What a cool project.
Yeah, that was that was really, really exciting. Just like using machine learning to sort of study physics, what I enjoy.
Yeah, it's like pure research.
Yeah. And then like playing around with all of these sort of modern things at the time, doing machine learning, and machine learning in physics and particle physics has been huge, I think. And
yeah. So was that your introduction to machine learning?
Pretty much, basically. So I was part of like a very good group and was supervised very well by a professor and a PhD student that sort of supervised me. And basically the year before I took like a deep learning in physics lecture, decided this is exciting. I want to do like a master's thesis in there. And in Germany, you're like embedded like for a year in the research environment. And it was great. We're allowed to basically do like lots of cool stuff and learned a lot. Basically, all of the stuff I know about machine learning sort of started off from this year at Aachen.
Nice.
And when you think about a use case like that, it's sort of the penultimate example of why you would need applied machine learning to solve a problem like that, because I imagine the data volumes that you're dealing with in detector systems like that are pretty large, and then your signal to noise ratio for measuring things like that, where you're talking about, okay, I have this matter interaction or high energy photon interaction with matter that then generates this cascade of particles that I'm trying to detect. Imagine scintillating out what you're trying to detect to say, and I have some history with this, because with nuclear reactors, those detectors are used as well for your primary coolant loop, and you're trying to detect like what is the ratio of fission byproducts that are happening within a core. For like research reactors, they do that, and those detectors are stupidly expensive, but they're single purpose. Like, you're detecting a very narrow band of radiation because of the limitations of the physical hardware and physics in general of how it's interacting with that detector. I imagine just getting that raw dump of data using photon detection and saying, where did this come from, is probably pretty much impossible to do by hand, certainly at scale.
Oh yeah, definitely. I mean, there's lots of like classical methods used like to even get the data into like a form where you can like even start thinking about doing like machine learning on top of it. There's like loads of details with like calibration and sort of like simulation of all of these electronics and cross validation going on. But in a sense, there was like a really good use case to use machine learning, because you have like sort of a detector grid, and you detect sort of time traces, like you have like pixels, and basically you get like video data more or less. So it works actually quite well with like convolutional networks, or like sort of like group FR and stuff, or transformers now. And like everything is noisy, everything is fuzzy. And there the challenge is like, I guess within any like deployed machine learning system, how do you validate that the stuff that you're doing is correct? You can do like lots of fun things and like lots of cool papers, but in the end, how do you sort of like test and verify that the stuff that you sort of did is sort of still valid? And then with this data, as you said, like I can't just look at the image or see, oh yeah, it's a cat, and it detected it as a dog. Stupid model. It's like, yeah, a bunch of like raw data. So you need to do like lots more analysis on top of that, and sort of also really understand your data. It's like a very sort of experimental process, and you need to get your hands dirty and sort of trying to do that. Luckily, I was just a master student and haven't, so like everything was already nicely prepared. But like the real stuff, there's like lots of details that are just need a lot of work to make these experiments work.
I think that statement really resonates with a lot of stuff that we've talked about, Michael, on the podcast, about building a team to do something like that, where you have hardware engineers that are building all that stuff. You have, physicists that are trying to understand a phenomenon that exists within the universe, and the ML folks that are working on the analysis and classification of events. How successful do you think that project would have been? It's just a hypothetical for you. If you had a team of 10 data scientists that just got that data as a dump and then said, hey, figure this out. You couldn't talk to a physicist. You couldn't talk to anybody who built the hardware. You couldn't talk to anybody who was working on the detector array. How do you think that would have gone?
I mean, I can only speculate here.
Sure.
And I don't think it would have gone very far in a way. I don't know. So some things might have been better, like the code might have been nicer. Well, let's say you get like actual engineers and like some things, but I think at the core with all of these things is all about understanding your data and understanding your sort of your distribution, or sort of the problems that you're actually trying to solve with sort of these physics experiments. At some point, I've thought more, okay, I'm not doing physics anymore here. I'm just like playing with TensorFlow and training models. But at the end of the day, it's all about like asking the right questions, designing the experiment, and understanding what I'm trying to measure. And in a very similar way to like in industry, where in the end of the day, it's all about like you're trying to solve a problem, or you're trying to sort of get an answer to a question. And I think that's quite crucial to have like domain knowledge in that. And I think we've seen that trend in general, and also like in academia and like research, where I mean, example like during COVID, we've seen so many papers like from machine learning folks doing like some great machine learning on some medical data. And we've seen also like medical folks like taking some machine learning and applying it to their data. And both of these approaches, like, I think don't really work very well if you don't really have like an understanding of like both the tools that you're using and sort of the underlying like math capabilities of your analysis chain. Yep. And also the domain area, because Like if I'm like now as a machine learning person, take some medical data, throw my nice model on it, like I don't know, I wouldn't measure something interesting or wouldn't be able to answer something interesting in a way. And the other way around, it's sort of, I've seen it a lot, sadly, like practitioners not understanding sometimes the limitations of some of these approaches with respect to uncertainty or just other things.
Yeah, you nicely reconfirmed something that both Ben and I think very strongly, which is collaboration between subject matter experts and data scientists is essential to build good tools. And specifically in industry, it's often going and talking to your sales team, your supply chain team, your whatever team, and using your expertise to apply solutions to their problems. And in your case, it's physics. And I mean, just thinking about Ben's question of 10 data scientists, I based on my explanation of the blue ball in the swimming pool, I think I would do a great job, but all other data scientists might struggle a bit without some physics under their belt. Yeah. Anyway, really cool intro to machine learning, and I wanted to ask you, how did you get into small models and quantization specifically? Was it a natural step, or was it via open source? How did you transfer into that field?
It was pretty at random, more or less. Like I stumbled upon Plumeride, a company I work now at, through a conference, and decided to join. Because at the beginning we did quite a lot of work on like extremely quantized neural networks, and like binarized neural networks, and I was able to do open source in sort of the first 1.5 to 2 years or so of the companies. We did quite a lot of work in open source, and sort of that just excited me. And so at the end of the master's, it was like, what should I do? And I wanted to learn more about machine learning, deep learning, and thought, okay, the best way is at least the best way for me was to join a startup and see how that goes. And I mean, like 5 years later, I'm still at the same company, so clearly something went well. Yeah, that's so. I didn't particular go into like small models or efficiency with like a concrete goal. Other than that, it seemed like a fun and interesting problem to solve. And yeah.
Yeah, and before we get into the technical, and the technical is super interesting, I've noticed that open source is now a really interesting business model for companies, and for instance, Databricks. And Ben, I was wondering your take. How has open source become sort of a linchpin for profit? It's free code. How can people make money off of it?
To echo some of the conversations I've had with Databricks founders, if your goal is to write some cool open source and then start a company, there's no harder business model for you to succeed with. It requires you to do two things that are almost impossible. One is create a super popular, critically important open source project, which if you look at the commits to Maven or PyPy, or heck, look at Apache Foundation projects, how many of those are still in use 3 years after they were first released? And how many of them, setting aside, crowd hype stuff with like GitHub stars, don't pay attention to that. It's all about downloads. How many people are downloading your package? And if you're curious, go on to Google. They maintain download statistics for pretty much all open source repositories. You can pull, you get a BigQuery account, even the free tier. You can query those data sets and see what your project is doing. And if you're thinking of starting a company off of something like that, you should be in the hundreds of thousands of downloads a week as a start. So it's like, hey, I've established street cred here. People know what this is, kind of, maybe in some niche environment. But then to make a successful company, whether or not it's open source or closed source, you still have to make a successful company. So coming from open source to a successful company, there's no causation there. It's two independent activities that the same group of people have to nail at the same time. So can you do it? Of course. Like, look at Databricks, its valuation. It's insane. There's other companies that started like that, but it's 0.1% of people that have submitted an open source package and then tried to start a company. They become successful enough that they can still pay salary for 10 years. It's hard. But if you have a great idea and you feel like, hey, part of our tech can be open sourced, do that while you're building your company. Like that's totally legit. Give back to the rest of the world. I think that's important. You're gonna have to create some sort of edge feature so that people are like, we're paying them to use, like, so that they manage this open source for us, or they build features for us that also go into open source. There's a lot of ways to do that, but people looking at a unicorn, and Databricks is a unicorn. It's very, very like a special place. Right time, right people, right ideas, right execution. If you look at that and think, I can replicate that, it's not trivial to do that. It's hard.
So for Plumer, were you guys starting from open source, or were you guys starting from closed source and then decided to open source Lark?
The fact that we open source Lark, that was something from the start, at least sort of like that idea was before I joined the company, already there. In a sense, we started out. So the goal of the company is still make very efficient models, or like basically make AI on the edge and on tiny devices possible. So in that sense, we sort of started out from the most extreme form of quantization and doing research in binarized neural networks, which is basically where I take weights and activations, and instead of having them in like float 32 or int 8, you just like have a single bit, which comes with some very interesting challenges if you try sort of to train these things, and in parallel building out the inference side, and also work on sort of the hardware side, in how to potentially put that into a chip form, into hardware. And sort of now we've taken all of sort of these learnings that we had from this, and sort of the setup that's sort of like rooted in a way in research, across like hardware, software, training algorithms, and our focus on sort of like smart home, on very tiny devices and microcontrollers. Like, I don't know, like on my desk there's like this tiny little board which runs a deep learning model on computer vision, which on microcontrollers is quite something unique. In the past, most of the deep learning models running on these devices have been either sensor data speech, which is sort of a much more, I don't want to say easier modality to work with, because everything has its challenges, but just the input data is already much smaller, which means just getting like a camera pipeline working that runs efficiently can sometimes be challenging on these things. So yeah.
Got it. So question, we're making models smaller. Does that mean that training time is faster and cheaper?
I mean, it depends. It depends. So sometimes it can take longer to train these models, but the good thing about these models is like we're not training billion parameters large language models that don't even fit on a GPU. So in a sense, like the core structure of the model is definitely smaller, and I think that definitely helps with sort of the cloud budget and sort of the compute budget you need for training these networks. And it also helps in terms of patience. Like I don't need to wait like 3 weeks for this model to finish training before I can sort of get an idea whether the model is sort of does something sensible. There's sort of certain things you need to do in terms of if you talk about quantization or pruning that might lengthen training time, but that's not inherent. That's just like limitations of like frameworks that we're using or sort of sometimes hardware support on the GPU side. I would say training tiny models is like a lot of fun because you can do like a lot, and you can train actually quite a lot of models also in parallel, which you probably can't if you train the next GPT-5. Probably don't want to run 3 runs in parallel just to see what happens.
Got it. Yeah. So the basis of the question was if we're using quantization to reduce the precision of your weights, theoretically, there's less information in each weight, and you would need more nodes. Is that correct?
Yes. However, I mean, yeah, there's just less information there, and sort of less things that this one value can represent. However, if you look at like many common architectures that are out in the field, I don't know, like ResNet 50 or so, these models, I mean, for now, current standards, quite tiny, but like for computer vision, still sort of fairly usable. These models are quite heavily over parameterized, so you would be surprised with like how much precision you can like reduce these weights and activations and sort of still keep high accuracy. Like in our current models that I'm training, like we see no difference between like let's say int 8 and float 32 if you do quantization aware training. And sometimes it can even help, like you sort of remove like a different like a class of problems. Like you don't have to worry that much about overfitting. Like it's a pretty good regularizer constraining your precision. And to make things efficient, it's not only about the weights but also about the activations. Does that answer your question?
Yeah, I think so.
I mean, I saw the same thing when playing around with images many years ago with some actual, deployed projects where your first thing that you want to do, if you're like, hey, I don't know what tooling I'm going to use here, and I certainly don't want to spend 3 weeks taking a whole bunch of image data, labeling it properly, just so that I can build a model to get a prototype out of, which is going to take 3 days to train, and it might not even do what I want it to do. So you go, oh, I'm going to take one of these open source models and I'll just, freeze everything up into the last like 3 or 4 layers and then, fine tune it. And we did that and we're like, wow, this is actually working really well. This is so much better than, the old machine vision that we were using before. Like TensorFlow is pretty awesome. And that was where our prototype stopped. When we went to planning out the project to say, what are we going to do here for production? And we were looking at the size of that deployed model. We're like, yeah, we can't deploy this thing on a VM or on Kubernetes and build all that infrastructure. Like this is going to cost a fortune to run this. So we decided to approach it with understand the architecture and the structure of the open source implementation that's generalizable. It's a generalized image classifier. Like, do we need this many layers and this many nodes? Like, is this even useful? So we did a bunch of tests, and we found out that the thing that met our needs was like 5% the size of ResNet, and with really good labeled data and some clever little feature engineering on the images, it was able to beat the performance of the fine tuning by a large margin. And it was dirt cheap. I mean, we probably could have deployed it to people's cell phones. It was so small. So I'm a huge believer in it. And there's actually people doing that for LLMs now, where it's like, hey, you have this specific domain, take a pre-trained model, but take the smallest one that they have, like the smallest version of it that has the least number of weights. It knows how to understand human speech and just train it on your specific domain. And it turns out it's faster, cheaper, and a lot of times more accurate.
Yeah, I think you make a very good point here. I mean, like for efficiency in general, I think we're at a very exciting time, because for a very long time, efficiency wasn't that big of a deal because just get like one additional GPU, like yeah, whatever. Now with these huge, I mean, I'm talking about the server side. On like embedded stuff, efficiency always was like huge. But what we're seeing now at like the complexity that you were talking about of like having a model that like, I don't know, my data science team trained on a Jupyter notebook or something, and trying to get that into Kubernetes, building all this infrastructure, the monitoring. If it runs on a GPU, then you sort of like you probably want to batch things. There's like a whole other set of things that you need to do on top. And moving it basically to the edge, if you're able to, like on the cameras itself, for us, computer vision on or on whatever device your user runs on, just like removes this entire block of complexity and DevOps and like worry. You still need some of it, of course, but
Right.
but it's not so model specific. And then the other thing that you said, sort of designing for like efficiency first, that's something I think that resonates super well with me, because also if you look at literature at big conferences, and what people are doing in practice, often you have sort of these reference architectures. And then you get a paper saying, oh, I can quantize ResNet 100 down to 1 bit or like 3 bits, and don't lose any accuracy. It's like, yeah, obviously not. I mean, not obviously, it's very hard work. I don't want to make any enemies in a way, but in a sense, it's like a kind of like a very obvious paper sort of to write, but whether it sort of meets these efficiency goals in practice, that's sort of then like another story. And oftentimes you're much better sort of starting from scratch. What's the problem we're trying to solve, and design an architecture and sort of like the whole inference stack with it.
So I've got a crazy question for you about edge deployment and edge computing in particular. A job I had many, many years ago was working at a factory that made the chips that go into smartphones. And when I started working there, we were a 45 nanometer process. That's how long ago this was. And now we're talking about, near UV photolithography that's being used to produce, sub 3 nanometer transistors. And these things are getting crazy. So computing power on a system on a chip that's deployed to a phone, and you could add 2 SoCs on a motherboard with not a lot of expense these days. Do you see a point in the next 10 years where a phone manufacturer is going to open up their SDK and their hardware specs to say, you can run arbitrary application code on an embedded GPU on this phone as almost a sidecar? If you had the capacity to deploy code instead of model weights to the edge, and had a framework where you could say, I want to be able to train a model specific for this exact piece of hardware, and have validation work for it, some sort of framework that would allow you to do that. Do you think that's where edge computing is moving in the future, for sort of like code deployment, and it'll generate model weights for you on the device?
I'm not 100% sure I understand your question, what you mean with code deployment, because if you have like all the engineering resources that you want, you can sort of already do that, right? You can sort of target sort of the GPU that's sort of like on the device. The question is then just like often like to which granularity. On like a CPU, we can sort of easily use like intrinsics and sort of like do like some D magic on accelerators, especially when you sort of have Android on top. Again, it's oftentimes sort of harder to sort of like specifically target these things. But what do you mean with like generate the weights on the device then?
Like actually do training.
Oh, you mean do training?
Yeah. So it collects the data from that phone for whatever, you don't want to classify people's pictures better, or do something with like, hey, I've seen the raw images that are captured and how somebody edits them on their phone. I want to be able to detect, like, per unique image that's created, a customized edit that this person's going to like, that sort of thing. And you need that training data. You can't just like fetch raw data. I mean, a phone company could, or some providers could, but if you're somebody who's a service that's deploying edge models, you're not going to have you're not going to be able to hit a Google API without paying a lot of money to get people's data like that for your training. And you wouldn't want to train, in the cloud, 1.2 billion models so that you could deploy them all to people's phones individually. That's not really an economy of scale thing. But if you took a code that you say, here's my training loop, run on the device in the background, do you think that's coming?
Yeah, absolutely. I think so. I don't. I mean, from a technical perspective, I don't see why not. I mean, federated learning and sort of research has been a thing for a while. I think at first it will start off sort of having existing models that sort of just adapt to user. I'm not very familiar in sort of that side of field. Like all I've done is basically have a model and it's sort of fixed once it's sort of on the customer's device. But I mean, even what you can do with like, just as you said earlier, like with just fine tuning the last layer, or like training linear classifiers on top of that, that doesn't really require that much compute power.
Right.
And I think the problems are there mostly in sort of the software stack to support that, less sort of on the hardware side. Mm-hmm. Well, you need, for many of these accelerators, you probably would need to have like proper int8 or like integer training if they don't support floating point operations. But for me, I guess like one open question that I always have about these things is like, how do you deal with like monitoring and validation? And I mean, like if I train a network now, I like look at my tensor boards or MLflow, or like look at my graphs and like see, oh yeah, there was a loss spike. Oh shit, I need to like do something else. How that process can be sort of like completely hands off and sort of ensure that this model doesn't get into like a weird state just because the customer's usage is not something that we have anticipated before. I think that needs to have like a lot of sort of like validation and sort of checking to see when we're sort of in like an area of like where this works. Sorry, I've rambled along, but I think that's how it's going. Yeah.
So SDKs that would allow for reinforcement learning with human feedback, as the user being the human feedback to say, I accept your suggestion, or change it this way. And then it actually gets that feedback and adapts its weights to create the next iteration.
Not sure if you want to do reinforcement learning directly on there, but
You'd need some
but
serious.
certainly adapting predictions or doing like a couple of training steps to sort of for like image generation things or so, if you sort of need to have a retrainable component. I definitely see that in the realm of technically possible. Yeah.
That monitoring system would be kind of crazy. Ben, how would you do it? So for reference, Ben has built 1 billion monitoring systems. And so
the monitoring system for edge computing where you're getting feedback in order to update your training code that you would deploy.
Yeah, would you basically send out the data to some server from the phone? Would you have some... Yeah, Lucas?
I don't think you want to send your data over the phone. I think that's the whole point of like doing it on device. Like I don't want to send my data.
It becomes kind of ironic. Like we don't want to send data to the phone, so we'll send data from the phone instead.
Well, you'd still want to have some sort of callback that's running so that the creators of the code would want a very stripped down metadata version of what the status was. So if you're looking at thumbs up, thumbs down from like the recommendation that was presented, the user liked that, you would anonymize that, get some sort of ID from your commit hash of your code that was sent over, and you would know the device, the hardware, like certain things about that device where this was run, and you would instrument that in an anonymized way to some centralized server so that you could look and say, how are our models doing? Because otherwise you're just operating in the dark, and you would have to offload that judgment to the device, which I personally would never do something like that. Like this fire and forget, you have no idea if you just shipped garbage to a user. How would you do a rollback? When would you do a rollback? Like that's something that I'm curious about. Lucas, how do you roll back for edge deployment?
So in our current, I mean, for our customers, what we do often, it's quite a lot of like testing in advance, and once a model is deployed, since it doesn't really change anymore, a rollback can be like done like any other over-the-air update for these devices. So it's not something that like adapts in an hourly way, right, and then sort of gets in a weird state, and we need to roll back. And
so you could do either a roll forward or a roll back by just saying, here's the actual, commit hash that we used for this deployment.
Actually, here's the binary. You sort of like ship a new binary.
Do you ever deploy to devices that don't have a connection to the internet or the world?
Yep.
How do you roll back on that? Go get the device and reinstall?
USB.
Well, so that's so what we would provide mostly the sort of the software and sort of the whole ML solution. So from my side, it's like, oh yeah, that's our customer's problem in a way. In some form or another, these devices will always be connected to something, because otherwise, why are you running this device? Unless it's like completely integrated, and then you would basically test it and just never roll back, I guess. But you will at some point for devices that sort of have like, I don't know, send notifications to your app or like a smart home camera or something. Like there will always be like an internet connection, at least at some point, because you want to give feedback to the user or send a notification or like stream a video to some place. So in that sense, you don't really have really that problem. But if it's really like a deploy and then sort of like forget in an isolated environment, you would need to do sort of like lots of pre-testing, or like you need to do lots of testing anyway before anything goes in production.
So we've been talking a lot about low-level MLOps and DevOps stuff. And I intentionally guided this discussion to this point just to give people a little taste of the super unfun things that we deal with as software engineers, where you have to think about all this stuff. Like, hey, how can I prevent myself from getting woken up at 3 a.m.? It's effectively what this is, or my whole team from getting on-call paged because fires are everywhere. When you came out of your master's program and came to the startup and started working on this, 2 questions for you. First one, how long did it take you to learn all this stuff? And secondly, how did you learn all this stuff?
That is a good question. When I joined the company, I was like the second engineer or so, at least from like the software side. We were like 3 people in an office. And with respect to DevOps or ML ops, if you're not providing a platform as a service or you're not providing a cloud service, you won't be woken up in the middle of the night because it runs on your customers' devices. More or less. I mean, there's still things that sort of can go wrong, but it's sort of not. So for the work I do, like we don't have like a sort of like site reliability engineers or so that need to do these kinds of things. So that's a great benefit, I think, of like running these things on device, because it will, like, and any kind of code that runs anywhere needs monitoring and needs testing. But I feel like, at least for me, but maybe I just don't understand enough about sort of the DevOps world. There's like just like a lot more things that could go wrong once you get a network involved. At least that's sort of how I think about that. And just like a lot more craziness once you get into load balancing and actually have like a system of like VMs at the end of the days. And then like, I don't know, containers that are deployed on top of that with like Kubernetes and some sort of scheduling. There's just like this entire state space that can go wrong, that you kind of exclude once at least your model part is out of the equation. So coming back to me joining the company, what we did set up quite fast, and that was actually, I think, like in the first, I don't know, month or so. I had experience with that before in like uni, sort of like managing the GPU cluster. There it was much more about getting a experimentation platform up and running, and getting us as like a team of like researchers, basically, or researchers/engineers, in a position to run experiments effectively and fast at a low cost, basically. Yeah, and I mean, that was a messy process. I mean, I can't lie. We took very early on the complexity of deploying to Kubernetes, just because the tooling we used sort of supported that as a runtime environment. So that was fun. We've never worked with like Kubernetes before. Sort of deploying that, getting all of that running. But basically, the only users is your internal team. So it's always between working hours. And if I'm on holiday and it breaks, well, then they would have to read a paper or have to go to the pub. I don't know. So it's not like there's a customer that is sort of dependent on this. But with the team growing, we've definitely had to sort of make all of this infrastructure much more stable. But for us, it was always like crucial that we get to a point where we can run experiments super quickly, to like get a fast iteration cycle. Like basically, I have my code, I change a line and hit run, and it should like get me a GPU, ideally like a spot or preemptible instances, because I don't want to like pay loads of stuff. And then you just need some logging, monitoring, and a way to basically make all of that kind of reproducible. And I think the world has moved on from like, I don't know, 4 years ago or 5 years ago, in like the tooling is much more sort of mature with that, like with like Kubernetes jobs or so, you can do now much more sort of like right out of the box. And so I think that to answer the third part of your question, it was all learning by doing. But yeah, so far that's also been for me always the easiest thing. Same with like open source or anything others. Like I never really liked or got motivated by sort of I'm going to do this tutorial and I'm going to learn Rust or so. Like that's I could never like sort of find the motivation to sit down and do like toy problems. So yeah.
Did that ever lead to any painful experiences?
I mean, I don't know. Like I feel like if you're in research or like in engineering or even in physics, at some point you build up quite a high tolerance of frustration level. So yeah, okay, this thing runs out of memory. Oh no! Now that you asked, we had like some very fun bugs, like just software running out of memory or like weird things, and then it ends up being, oh yeah, I need to use this different memory allocator, and it's like that's just something that you would have never thought of before, and sort of you acquire, and then you like call support or like end up messaging on like GitHub issues. So in that sense, like I think these things have been sort of the painfulest thing for me. If my model doesn't train, it's sort of like I know where the problem is. It's like sitting in front of the computer. But if something isn't working as it's intended, I always felt like it is something very unsatisfying if the thing that you're trying to do that should be supported just kind of doesn't work because of some code error that's sort of like not within the code base you control, but within the code base of like some open source project or some cloud provider that just doesn't do what they write in their documentation or some. I think for me, these have been the more painful things in terms of like, I don't know, cluster going down. Yeah, at some point it was reasonably stable, and then before that, actually, my colleagues did go to the pub once on a Friday afternoon when everything went downhill. But that was a long time ago. That doesn't happen anymore. So now our infrastructure is much more stable.
Good. Yeah, and follow-up question to that, although the pub does sound really nice. Follow-up question. When I first joined Databricks, my ability to sort of iterate in a sequential manner was not amazing. And that was a focus when I first joined, which is basically I want to be able to do trial and error type of things and have every single trial be of high quality so that when I get data returned from that trial, I can take the next step. And so an example is if you're trying to find a number between 1 and 100, you always split in the middle until you get to your number. That's the most efficient way. And it's sort of the same process for problem solving. So both of you are successful professionals, very smart. I was wondering what % of the time you guys do sort of this trial and error approach where you're like, this new memory allocator, let's fricking see if that helps, versus actually going and understanding the root cause and having a pointed solution? Or is it sort of somewhere in the middle?
I could take this at first. So exactly as Lucas alluded to, we are a customer-facing organization. So the group that I work in, we have that severity measurement for anything that goes wrong. It can be the docs are wrong. Okay, that's a Sev 2. We'll get to that in a week. There's other things that are higher priority. And then there's, I can't save my model. I just trained it. I can't save it. That's a Sev 1. Like, hey, something's broken here. I need to do something about this in the next couple of hours. And then there's I can't do anything with ML flow. That's a sub-zero. That's bad. That's an incident, and usually due to a regression that we accidentally shipped. So the reason I'm talking about severities and responses is that your first response, if you are running a service, is to mitigate. And that mitigation can be what changed recently, roll back now. Just revert to previous good known state. I don't care about the root cause right now. Just get it working now. Fix the problem. I don't care about fixing the actual cause of the problem. I just need to get the system into a state that works again. And you've seen me do that actually, Michael, where like releasing a patch release that just reverts like 4 PRs. Did I know which one was the root cause or what the mechanism was for why it failed? No, but I know that I did that system of trial and error that you're talking about, that binary search approach where I take the bad commit history, run the code that should work but doesn't work, verify like, yep, this is totally broken. Revert 6 commits or 8 commits or 10 commits, go back 4 days on the state of the master branch, build a branch off that, run it. Does it work? Yep. Okay. Go in half again. Broken or not broken? And you just kind of get a feel for where was the state of this that was good, and then release that, like patch release, fix the problem. That gives you breathing room now to go and do a root cause analysis. And if you're investigating something as a professional software engineer, you have to do an RCA. You need to know what went wrong, not to say, hey, Jack broke this, Jack sucks. That's not helpful, like at all. It makes Jack feel really bad and makes everybody else feel really bad that blame is being thrown. Should never do something like that. If anything, you can point a finger, it's at the tech lead or whoever's in charge of running that team, because they let Jack do that. They let Jack down. They let the team down. They let the company down. And as a tech lead, you are responsible for that. It's your problem. But a proactive approach for this is figure out the root cause, because you want to make sure that a system is now put in place, or tests are now put into place, or something that safeguards you from allowing this to happen again. That's the real key. I don't know if that was exactly what you're asking, or if you're asking about like how to figure out how to build a feature or something, but you can even use that sort of approach, that thought process to when designing stuff too.
Yeah, it was on the feature side, but like you said, it applies to features as well. But yeah, Lucas, what's your take? How do you guys do it?
So since I'm more on the R&D side, I have the luxury that like these sort of like super fast incidents response only rarely happens. And if there's something that's critical, obviously that's sort of the first thing, like Ben said, revert and pray. While Ben was talking, I've been trying to think of like sort of the thought process that sort of goes through my head. And I think the first thing obviously is like sort of this frustration of, I'm just like trying random things. I think that especially in ML, that's like some like very, or like in stuff that you don't fully understand down to sort of like the lowest level is sort of often the sort of direct reaction. It's like, this thing doesn't train. I don't know, I'll double the learning rate or half the learning rate, or like add some weight decay, clip some gradients, reduce the batch size because it runs out of memory. I do that, of course, but I've often find it like quite like unsatisfying. So there's like sort of two approaches. If it's like a code problem, I usually just like, if it's open source, I look at the code. That's the first step. And then just like try to understand really what's going on and sort of like, what is the underlying problem? Often down to like, okay, this commit by this open source project like 3 years ago introduced that, that's the problem. We can like, that sort of like gives me kind of comfort. And it's like, as working in a company versus like being a student or like working in open source, sometimes there needs to be a limit to that. Like, is it actually important that I know, or is it like, is the workaround good enough? So I've definitely had to learn that when like joining a company, like what to investigate and what to just work around in a way. And then the other thing is sort of like the root cause analysis that Ben was talking about. Yeah, I think it's sort of like I feel my background in physics sometimes shows it's like all about, okay, let's design an experiment, and then basically try to simplify and try to remove as many variables as possible. So like, I mean, it is a bit of a trial and error, but then it's much more sort of, I think sometimes much more targeted. And then over time, you sort of working at like a code base that either sort of you own or sort of like working with a tool like PyTorch or TensorFlow or so, there will be sort of like little hunches or sort of little areas that you're uncomfortable with. And so that might be then sort of a thing that will lead you to prioritize one experiment over another, or like some experience in the past that where something similar went wrong. But that's not really about how to design the experiments, more of like, how do I prioritize where to start? And it always helps to ask colleagues, like go for a coffee, explain them the problem, or ask for help. That's usually step one, or sort of like once you're at the point where you're able to explain the problem to someone, which can sometimes be very difficult. Like writing a very good issue on a GitHub repo is something that is surprisingly hard, and a reason why I often send a pull request first instead of like actually writing an issue, because it's oftentimes easier to fix the code instead of trying to explain very clearly what went wrong. Anyway, I'm not sure if I answered the question, but I think that's sort of like the thought process behind that, if that makes sense.
Yeah, I think that answered. It's funny to hear both of you have like sort of different approaches. My approach, and I think it's very subject specific. So it seems like, Lukas, your trial and error is exploration almost. You're collecting data, and then you always go back and do a root cause analysis and determine why the data said what it said. For me, I I work a lot in sort of a consulting capacity, and I'm often given subpar code repos that are just very difficult to understand, and I frankly don't want to understand them. So if I can get a green check mark to make it run, oftentimes I'm very happy about that, and so is the customer. But for really important things that are mission critical or that require maintenance, yeah, you need that root cause analysis. You need to go deep and actually understand what was the problem and how to resolve it. But sometimes for little prototypes, iteration is what I do, admittedly.
I mean, one thing to add onto the feature definition aspect of it, I mean, I just gave you the task the other day, Michael, right? You're going to be building a flavor in MLflow, and there's a bunch of design considerations that you have to come up with. And the way that you approach that, or the way that we do it at Databricks Engineering, is through design docs, where we do a bunch of prototypes, but it's informed prototypes. And it's exactly the process that Lukas explained, where, I don't know, Databricks isn't filled with physicists, a lot of computer scientists, but there are some physicists. But it's all using the scientific method and around designing of experiments where you're doing exactly that. If you broaden the decision of how to build something to infinite possibilities, to say, we could do any of these different ways of building this collection or iterating over this collection, there's, in any given language, there's probably thousands of ways to do that. if you get creative enough. You could do some crazy stuff in even high level languages. We don't explore all of those. We just say, what are the simple ones, or what's something that I know for sure based on my own wisdom and experience, I know this is going to work. It's probably not the best solution, but it's the first thing I'm going to prototype and show. Like, does this actually work? Does the code execute? Yep. Okay, I've got that in my back pocket. I now want to explore something maybe a little bit more complex, but potentially way more performant. And I'll do a prototype of that. It's pseudocode usually, like a repro of something very simple. You're not implementing something for production. But then do that, show that, and then start weighing the trade-offs. So then you're going into the analysis of experiments. I've done these 5 experiments and collected the data associated with them, with like code complexity, maintainability, readability, as well as performance. Like, how long did it take to run? How big of a collection could I send through this, and how long did it take to run? If we're talking about some like network IO thing or memory allocation space thing. And once you have those 4 or 5 things that you've tested out, then you go for peer review, just like you would in the scientific process. You get other experts to weigh in, and people will vote. Some actively vote with saying, yeah, I agree with your conclusion that option 2 is really good. Other people vote with their feet. They just either they think that the idea is really stupid. That can tell you something as well. Or you're going to have people that strongly do not agree with your conclusion. And that's why it's important to have that data there to back up, and you challenge them. You say, here's the data. Please explain to me with your hypothesis of why this is a bad decision. And that's how you learn. They might have context that you just aren't privy to. You're like, oh, I had no idea that we needed to integrate with this other thing in another 2 months. Yes. Okay. Option 3 is better here. And then move on. And then you go and just build option 3.
Yeah. That sounds about right.
You'll see, you're gonna do this over the next 6 weeks, man.
Woohoo.
I want to add one more thing about sort of this you have like a bug or something goes wrong or something unexpected happens in lately. Let's say I'm in the development stage or either some like very complex code or some project that I plan to maintain over a longer period of time, or I'm developing a machine learning model that's not just like a quick prototype that needs to go out of the door, but something that will become a basis of something to work on and like keep improving over a long time. I've actually always had a quite like a positive feeling if something really goes wrong, because that just like means there's something I don't understand, and there's something like we either conceptually don't understand, or there's like something to learn in sort of in that area. So I think that's always quite something that I find exciting about to really investigate. The only times where this comes frustrating, I feel like, is if it's like something that I think, yeah, no, this should really work. It's like sort of like some fundamental infrastructure layer is like broken in weird things, or like some supposedly stable API doesn't do what it says on the tin. That can be very frustrating. But sort of for the type of things that are a bit more exploratory or a bit sort of still in the very early development phase, I find it that is quite can be quite fun and sort of like very interesting also to debug these things.
Were you always like that?
I don't know. I mean, like in if I think back to like uni or so, like there's been like definitely like days where like 5 people sit on like this sheet of paper that like thousands of students have solved before, and you have no clue. And I guess after like doing that for a couple of years, then it's sort of like, yeah, okay, it's fine that I don't know this right now. I'll hopefully know next week, or yeah.
Hopefully, yeah.
Yeah. No, I always find it quite positive, because it's like there's something fun happening, and I know my idea of fun might not be everyone's idea of fun, but yeah.
Yeah. And just one note before we wrap. I know we're over time. You can train that. You can teach yourself to enjoy the failure and enjoy the pain. Like it's a really interesting process, and I suggest you sort of explore rewarding yourself for breaking stuff. I've done that. I've did a day literally this week where if I broke 5 things on this project, I would order myself takeout sushi. And that sushi was delicious, and I loved it to death. So whatever motivates you, adding rewards is definitely a useful tactic.
I mean, the weirdest thing is if you want to break something and it doesn't break, then I'm really confused. So like you say, okay, now I'm like
That's a good point.
100x the learning rate and it doesn't break, then my confusion starts.
Yeah. The flip side case is really relevant as well. Like stuff should break where it should, and if it doesn't, that's also not understanding. So
Unless your repository is just full of a bunch of dead code, which I'm sure you've seen those repos, Michael, in your line of work. I know I did when I was doing your job. Like, yeah, this is cool. This is 30,000 lines of code in a single document. Why would you do this? And how do you find anything? And then you prove out that an entire function is never called by just saying assert 1 = 0 in like within the function call itself, and then run the entire like from main, and nothing fails. And you're like, see, please review your code base for like copy this whole thing and put it in an IDE, turn on the linter and see what shows up. And it's just Christmas tree of just red everywhere. Like, yep.
yeah. Yeah, no, I actually have never seen that. In the 18 months since you left the field, all code is solved. Cool.
Uh-huh.
So
I mean, one thing that oh, sorry,
no, go ahead.
One thing that I've always surprised me, or like sort of like something that I didn't think about when I like started out, is like how long code actually lives. Like it never dies, and it sort of never gets removed. Well, sometimes it gets removed, but like some piece of code I might have written 15 years ago. Well, not quite 10 years ago, let's say. Still around. That's crazy, and it applies to sort of so many of these tools we rely on. I find it quite fascinating.
Yeah, it's a good point. It's sort of alarming how code you wrote as like a junior in high school is still running in a production system. So
well, we had that lady on like a year and a half ago on the podcast who, before we started recording, she was talking about stuff that she did back in like 1975 on these mainframe systems. That was the foundation for a lot of the solvers that are now used in TensorFlow, PyTorch. So that the low-level libraries that are used for mathematical computations that are written in Fortran, she was on the team that was writing that stuff. And it's like, talk about longevity, where your code lasts 50 years without modification. You can still go to that source code and look at it, and it'll have a date that this thing was committed. And you're like, that's before I was born. That's crazy. And it's still running.
yeah.
Yeah, not many people realize that. Like, if you use SciPy, yeah, you're using lots of this Fortran code, probably.
Yeah. Cool. So in summary, lots of really interesting notes here. We actually didn't talk about tiny models as much as I had hoped, so maybe we'll just have to do another episode. But the things that stuck out to me were, first, collaboration between subject matter experts and data science experts is often necessary to correctly solve a problem. In terms of open source, if you're looking to start a super successful company, you probably shouldn't start with an open source library. But also, if you're interested in seeing what your open source library is doing, you can just go to BigQuery. There's a free tier. It'll show you what's happening. On the tiny model front, int 8 versus float 32 can have identical accuracy, and Lukas has been proving that out with his work. The thing that, or the sort of the purpose of quantization is it's faster to train, it's cheaper to train, and honestly, it can generalize better because there's less weights and it's simpler. And also on-device training is coming. Then finally, on solving problems, if you're accountable, the first thing you should do is fix a problem, get your system running again. But root cause analysis is an essential final step, whether it be via data collection and sort of learning about your problem, or just building a maintainable, robust solution. You really want to know why stuff broke and why your solution solves what it's solving. So, Lucas, if people want to learn more about you, small models, your company, whatever it might be, where should they go?
Yeah, about Plumeride is plumeride.com. You can sort of find all of the stuff we're doing on there. Some really nice demos as well, running in the web browser, not on tiny devices, but at least running locally there. Yeah, about me, you'll find me on GitHub, like L Geiger is my GitHub handle. I'm not so active on social media, but you can find me on Twitter with like an _ L Geiger. Other than that, yeah, I'm sure that we'll put links to the profile in the description. Yeah, it's been a pleasure to talk to you. First time on a podcast, it was very exciting. I had a lot of fun.
Yeah, thanks for showing up.
Yeah. So until next time, it's been Michael Burke and my co-host,
Ben Wilson.
and have a good day, everyone.
We'll catch you next time.